Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed the competition model, where we have considered like Lotka-Volterra equations, and in that model we have discussed like the stability analysis based on null clines and Jacobian matrix and like phase diagrams. And also we have discussed the comparison of different models there, like for the stability analysis, how we are just using this phase diagrams or null clines, whether we can have a qualitative analysis with the exact solution that we have also made. And this is the final lecture for this one, and here we will just discuss this continuous time prey predator model. And in this model also the same prey predator model we will just use, but some modifications we will just do, adding some terms. Then we will just go for the stability analysis of this modified model, and finally we will just go for the phase diagram. Since in the last lecture, if you will just see, we have discussed about Lotka-Volterra competition model, like if more than one species, if it is present, either it is like a interspecific or intraspecific, they will just compete each other for the like resources or like to survive over there. So two or more species if it is present, then especially we are just using this competition model. So they can just compete for resources or habitat. So either one of them, if it will just justified, they can just we can just say that is a like competition model. And in this lecture we will just study another form multi-species model, where one species are prey and another species are acting as predator. But this kind of models were also discussed by Lotka and Volterra. Specifically they are known as prey predator model. If you just recall this discrete time models for the same, you can just find that we have used like different forms of mathematical formulation there. So in order to formulate this model, we will just relate these biological aspects with ordinary differential equations in stepwise procedure. Let us consider suppose two species N1 and N2, where N1 is acting as prey here and N2 is acting as a predator. And the growth of N1, that is prey, is accelerated in absence of N2 or the predator. This means that if predator is not present there, then this prey will grow it of like geometrical form, or in a exponential form it can just grow it off initially. Since like initial resources or the food is available to them, then directly if there is no decline of that population, then they can just grow it off. While growth of a predator, then if predator it is present there, they can just eat the prey and they can just decline this prey population. And this predator population, if suppose sufficiently this prey will be reduced, then this predator is declined rapidly in absence of a prey. Initially in the last lectures also I have considered like one example, like suppose deer population if it is present and some tigers are there. So then when this like deer population will be huge, then tiger will eat the deers and they can just grow rapidly. And once this population of deer will be like less, then this again this tiger population will be less, since this tigers will fight each other to get this deer for their food. And if we assume suppose growth or decline rate as exponential in nature, then we can just formulate this model as like dn1 by dt, this equals to like an1 here. Since directly if you will just get the solution, it will just represent that n1 equals to, we can just write as a e to the power like n1t here. So exponentially it will just grows it off with respect to time, if you will just see. And if you can just find here that A means we are just considering the growth rate of prey and C is the decline rate of a predator here. And if you will just consider here predator, predator means like suppose N2 is the predator here, and if we are just considering that they are also decaying exponentially in absence of prey, then we can just write this model as a dn2 by dt as minus cn2 here, where already we have considered this like growth rate of prey or decline rate of like predator, it can be considered as positive. they cannot be negative. So, in this system, if you will just see, we have not considered the interaction between prey and predator. This means that both these equations are independent to each other. And if you will just consider like interaction between prey and predator, then preys will be eaten out and hence will affect their growth rate. And similarly, if a predator will eat prey, which will help in their growth. So, that is why we can just say here B and D are factors by which growth of prey and predator will get affected respectively after interaction. And if we will just consider this interaction will be modeled as a product of population, since individually if you will just consider like one tiger, just they are eating like 2 deers at a time, then individually we have to consider like this predator population or the prey population, they are affected by each other. So, that is why we have just considered that when this predator population they will just grow it off, then this will just show a decline of this prey population. Similarly, if this prey population will be like sufficient, then this predator population they will just grow it off. So, that is why we have just considered there is a decline rate of prey here and there is a like a positiveness of this population growth in predator here. And here we have just written here minus B signifies the declination of a prey population and plus D signifies the increment of a predator population in interaction. Since if you will just see that sufficient amount of a deer and sufficient amount of a tiger if it is present there, so no other predators are available there, only tigers and only deers if it is present, then sufficiently they can just like tigers can use this deers and their population can grow it off, but in the meanwhile you can just find that this deer population will get reduced. So, that is why this is minus B and this is plus D here. So, if you will just find here to find the steady states of this model, if you will just see that we have just considered here this model as a dn1 by dt equals to 0 and dn2 by dt this equals to 0. So, then we can just find that if I will just take common here directly n1 into a minus b n2 this equals to 0, and similarly if I will just take common n2 here, I can just write minus c plus dn1 this equals to 0 here. Obviously, I can just write here either n1 equals to 0 or like a minus b n2 this equals to 0, which will just provide you here like n2 equals to a by b. And similarly, if I will just consider the second equation here, then that will just provide you either n2 equals to 0 or minus c plus d n1 this equals to 0 here, and which will also provide like n1 equals to c by d. And to achieve these critical points, especially we will have these points like n1 equals to 0 and n2 equals to a by b, and n2 equals to 0 or n1 equals to c by d here. So, obviously, the steady states points are like 0 0 and c by d a by b here. And if you will just formulate this Jacobian here, then we have to take this differentiation with respect to first n1 for this equation, since this is nothing but we can just write f of n1 n2, and second one we can just write this one as a g1 n1 n2 here. So, for the Jacobian first we will just take the differentiation of f with respect to n1, then for the second element we can just consider the differentiation with respect to n2. So, that is why if you just write directly the model here, then we will have like first one that is in the form of n1 dash, which is written as a n1 minus b n1 n2, and second one if you will just see, it is written as n2 dash, which is nothing but minus b n2 plus your c, sorry, this is c, this is d here n1 n2, yes, minus c n2 plus d n1 n2. So, if I will just take this differential, since I am just considering here this is as f of n1 n2 and this is as a g of n1 n2 here, And first I am just considering this differentiation of f with respect to n1, then I will have this value like a minus b n2 here from this equation. Similarly, if I will just take this differentiation of f with respect to n2 here, then I will have like minus b n1 from this term here. Similarly, if I will just differentiate g with respect to n1 here, I will have this term as dn2 here. Similarly, if I will just take the differentiation of g with respect to n2, I will have minus c plus dn1. And for the steady state, if I will just put directly as n1 equals to 0 and n2 equals to 0 here, then I will have these values. From this equation I will have a only, and from this equation I will have minus c only, and the rest of these quantities are 0. So, that is why I will have this Jacobian as like a, then this is 0, then this is 0, this is minus c here. So, that is why I have just written for steady state 0 0, Jacobian represents the diagonal element as a and minus c here. Since J is the diagonal matrix here, and this is like a diagonal matrix, so the eigenvalues are nothing but only the diagonal entries here. So, the diagonal entries are nothing but a and minus c. So, that is nothing but the eigenvalues here. And for the steady state, if you will just see here, one eigenvalue is positive and one is negative, that represents this is a unstable state. So, the steady state 0 0 is unstable because one of the eigenvalue a is positive here. This means that if you will just see the phase diagram, we can just find that one of this value, since minus c it is present along the like n2 axis. So, it will just push towards this 0 0 point, but this x axis, if you will just see, if I will just directly put here as like this is suppose n1 axis, this is n2 axis, directly I can just find that at this level you will have like these arrows will go out. But in this level, if you will just see, this will just move towards the 0 0 point here. So, hence the like phase diagrams, it will be like come this way and then it will just go outwards here combinedly. Since this is negative, so it will force towards the 0 0 point, and since it is positive, it will just take away from these points here. Again, if you will just go for this steady state analysis for this point like c by d, a by b here, then directly we can just find that if you will have like a minus b n2, b n2 means if I will just put directly n2 as a by b here, then it will just cancel it out. So, it will have like a minus a. So, that is why this is just giving you 0 value here. Similarly, if I will just put like n1 equals to c by d, I will have this value minus b into c by d here. Similarly, if I will just put here n2 as a by b here, I will have like d into a by b. And if I will just put here n1 equals to c by d, so then minus c it will just cancel it out. So, this will just provide you 0 value for this term. And if I will just see for this like eigenvalues here, then these eigenvalues are nothing but if I will just put here as a minus lambda here, and its determinant equals to 0, then it will just give you like lambda square plus AC equals to 0. This is nothing but the characteristic equation at the steady state point c by d and a by b here. And if you just see these eigenvalues, so they are nothing but this like iota values like square root of AC here. Since this is a complex root, so we will have like plus and minus sign here. So, since the eigenvalue is purely imaginary, we will have like the steady state is stable here. And if you will just see here that the real part of this eigenvalue is 0 here, this means that this represents a non-hyperbolic function, or we can just say it is a non-hyperbolic steady state by analysis of Hartmann-Grobman theorem. Hence, if in this state the Jacobian will not give the actual phase diagram, we need to go for Lyapunov function. And the formulation of same need the concepts beyond this course, and which we will just try to skip in this section here. Since this assumption of this like functions we have to consider, then we will just consider like the 0 value at the 0 point, and outside that point we will have like a greater than 0 value, and then we will just go for this derivative values where it can just have a like stable value or where it will have an unstable value, that it is not we are discussing here. So, if you just go for this phase analysis or the phase diagram for this eigenvalue for this C by D and A by B point here, we can just find that at 0 0 point, definitely if you will have like a no prey, no predator, then we will have a unstable condition. And if you just find suppose lambda equals to plus or minus I square root of SC, already we have discussed in the earlier lecture that it will just form this elliptic nature, or this phase diagram will just represent this elliptic shapes there. This means that it just follows like when this predator population they will have like grown it of level, then suddenly this predator population they will just grow it up also. And after that we can just find that there will be a decline of prey population. So, then again we can just find there is a decline of a predator population. So, that is why it is just following this elliptic shape. And exactly if you just see this actual phase diagram, we can just find that this figure represents the actual phase diagram of this prey predator model here. And for this C by D and A by B point, we can just find that this represents the stable point for this prey predator model here. And if we will just go for a further analysis of this prey predator model, the elliptical behavior already I have discussed in the previous slide, that steady state shows that both the species will be cyclic in nature, since if we will start at any point we will just come back to the same point. Biologically if you will just visualize, then we can just find that the certain size of a population of prey and predator if you will just consider at a level, if prey population is less, then it will just force the predator population starving, and hence their population will start decreasing. And when predators are small in quantity, we can just find that it will make the prey to live happily and their population will grow it off. And when they will be sufficient amount, then predators will find their food sufficiently and they will start growing again. So, we will have a like a repetition of this cycle. So, if you just visualize in a graphical sense here, we can just find that if certain amount of prey if it is present there and certain amount of predator if it is present there, definitely you can find that initially less predator if it is there, then this prey will just grow it off. Since less prey, so that is why they can just eat less. So, that is why this prey population they can just grow it off. And finally, we can just find that prey population it will be maximized suppose, then this predator population it is just growing it off. And after one level you can just find that if the predator population has like greater than the like carrying capacity, they can just eat sufficient prey, then this prey will decline. But at that level you can just find that this predator population they will again grow it off. And after certain level if you will have less prey suppose, then this predator population again they will just get it decline. So, that is why they will just follow a like cyclic nature. And if you just go for further analysis of this prey predator model, now you can just think that can this happen in real, especially it would happen in real, the ecology will always be balanced. So, the actual system should be in such a manner that it should convert to a steady state. Since if you just see in this diagram here, always it is just coming towards a definite point there. So, there is a need a special modification of this model, since especially if you will just see this model here. So, this ecology should be balanced, neither we can just find there will be no population of prey or there will be no population of a predator. So, that is why we need some modification for this one. Now, if you will just consider this new model by this logistic growth population instead of this exponential growth population, then we have to like modify this model as like dn1 by dt. This can be written as like we will have a maximum carrying capacity, that is k here. So, we have balanced this equation in the form of k minus n1 by k here. This is the only modification we have just done from this earlier equation, if you will just see. So, in the earlier equation we will have these terms like dn1 by dt, this is nothing but an1, that is the exponential growth we have just considered, minus this decline rate due to this predator population. Similarly, we will have this predator population as dn1 by dn2 by dt, this is nothing but minus of bn2 plus, sorry, this is c here, this is a d of n1 n2. This predator population grows due to like prey presence. And we are just modifying this term since we have just defined in this model. If you just see in the cycling process, we will have a like maximum carrying capacity here. So, for that only we have just added this term, that is 1 minus n1 by k, or you can just write it as k minus n1 by k here, which can just balance this population of a prey in presence of a predator. So, then if you just go for like further analysis of this modified model, instead of this exponential growth, if you will just considering here logistic growth model, then we can just write this one equals to 0 and this one equals to 0 here. Then we will have first term as n1 equals to 0 for the steady state points, second one we can just find it as n2 equals to 0 here, and the next one we can just find the same one as like minus c plus dn1, this equals to 0, we will have n1 equals to like c by d. Similarly, if I will just take the first term here n1 equals to 0, then I will have remain term as a into 1 minus n1 by k minus b n2, this equals to 0. If you will just see the same thing, it has been written here. And if you will just see here a minus a n1 by k minus b n2 equals to 0. So, this you will just provide, if you will just combinedly consider all the points here, we will have this simultaneous equations, that is the steady state points are 0 0, next one is suppose k 0 here, and last point is a c by d and a by b into 1 minus c by dk here. Observe that the coordinates of steady state must be positive. So, if you will just give here k greater than c by d. So, c by d is nothing but it just represents a ratio of like a decline of a predator in absence of a prey, and which should be greater than 0 here. And if you just consider this Jacobian model, so then this Jacobian model, if you just consider this equation that this is suppose f of n1 n2 here again, as I have explained in the earlier slides. So, this can be written as in the form of g of n1 n2 here. And if I will just differentiate f with respect to n1, so that will just provide you the term this one, and if I will just differentiate this f with respect to n2 here, that will just provide this term here. And if I will just differentiate this g term with respect to n1 here, I will have the term as a dn2 here, so dn2. And if I will just differentiate this one with respect to n2 here, I will have the term minus c plus dn1 here, minus c plus dn1. And for the steady state 0 0, if I will just see the Jacobian is nothing but the same one, I can just get it off here, since n1 equals to 0, n2 equals to 0, n1 equals to 0, n2 equals to 0, n1 equals to 0. I will have the remaining terms a and minus c in the diagonal position. So, one of the eigenvalue, if it is positive, then we will have like a unstable situation in that steady state point. And for the steady state, if you just see here, since we have just considered k is the population for prey here and predator population is 0, the Jacobian will just take this value as minus a, minus bk, 0 and minus c plus dk here. And if you just consider this maximum carrying capacity, this is greater than this like rate of decline of this predator population in the absence of a prey. So, then the positive eigenvalue minus c plus dk will make the system unstable here. And if we will just find the Jacobian for this steady state c by d A by B into 1 minus C by dk, the Jacobian can be written in the form of like minus AC by dk minus BC by D and D into A by B into 1 minus C by dk, and last value is 0. And if you just take this trace of this Jacobian matrix, trace is nothing but the sum of the diagonal elements, which is nothing but minus SC by dk plus 0 here, which is less than 0 here. And if you just see this determinant of this matrix, then this determinant is greater than 0. Hence, we can just conclude that both the eigenvalues are negative. Hence, this steady state point is representing a stable point here. And if you will just go for this analysis on a prey-predator model here, and if you just plot the null lines for this function here. So, we will have the steady state points as 0 0 here, and we will have this steady state point k 0, and another steady state point if you just see here, that is nothing but C by D and A by B into 1 minus C by dk here, that is nothing but this point here. And we can just find that the null lines here, that is just intersecting each other at this point also. And as we have discussed in the earlier lectures, that this will also give you a steady state point here. And if we can just consider that k 0 is a stable point here, then we can just visualize that if there is a sufficient amount of presence of prey is there is no predator, then we cannot find that the decline rate of, like, since we have just considered as a C by D is less than k here. And in that scenario, we can just think that rate of decline of predator population in absence of prey, that is less compared to the presence of prey here. So, that is why this is an unstable point. And this is giving no intersection points of two non-trivial null lines. And if we will just consider also sometimes, suppose if in a mathematical point of view, if you will just generalize this equation, then if you will just consider, suppose k is inside, suppose like in this interval, this means that C by D is greater than k, suppose. In that scenario, we can just also find that this is also a unrealistic situation. Since C by D represents this like rate of decline of predator population in absence of prey, but here prey is present there and k is present, then we will have a like unstable situation. So, that is why we can just say that this is giving no intersection points of two non-trivial null lines will forcefully make steady state k 0 to be stable, means no involvement of a predator here. So, this is unrealistic and mathematically we cannot achieve also that one. And if you just see here all other points, like different points, if you just see here that below these points, if you just consider, then it will just take this shape that the value will just go upwards. And if you will just see this physical scenario also, always it will just formulate a cyclic procedure to come towards this convergence point here. And in this model, we have discussed like the modified prey predator model, where like two species are present, that is prey and predator. Then we have discussed about this stability using the Jacobian matrices. Then we have discussed like null lines and phase diagram for this model, and realistic nature of this model using logistic growth of prey and species. Then the spiral nature of this prey having logistic growth. And if you will just analyze the total lecture series here, then first in the mathematical models we have just discussed like a deterministic and a stochastic process. And in that models, first we have discussed like a discrete time system which involves like difference equations. Then in the second phase we have started like a continuous time system which involves like ordinary differential equations and partial differential equations. And in that we have discussed like growth of microorganism, and based on that we have developed this chemostat model, and we have analyzed that model using null line analysis and phased plane diagrams. So, first we have discussed about the single species model, and it can be like intrinsic growth rate function or axiom of parenthood. Then we have just considered for this single species model in a exponential growth model, then the logistic growth model, and finally, we have just considered a special case model that is called Ali effect. And if we have just discussed this one in two species model, then that deals with Lotka-Volterra competition model, where we have just discussed this introduction of competition models for like species more than one. And then the analysis has been made through this phase plane diagram and Jacobian to find this stable nature of the system. Then this condition of coexistence of species, and in each of this coexistence or like competition models, we try to visualize this mathematical phrases or these diagrams or this analysis through this biological meaning, and we try to establish this relationship of this mathematical expressions with this biological like scenarios. And in the last phase, we have just discussed this phase plane diagram and Jacobian for prey predator models. And if you will also analyze this one in a qualitative approach, then you can just find that this phase diagram analysis we have made for one dimensional ordinary differential equations to check the steady state. There also we have just find this slopes, whether the slope it is just representing a positive nature or negative nature. Based on that, we can just say that whether it is has a stable solution or not. And for the 2D system, we have discussed both for like a coupled system and uncoupled system, and how this eigenvalue is behaving in case of like the stability choosing or the stability nature of the system in a 2D uncoupled form. And in the coupled form, we have just analyzed the nature of eigenvectors there, how they are just like behaving inside the system, and based on that we just try to analyze this like stability or instability nature of the system. Then in the 2D coupled system, we have just defined these eigenvalues to find the saddle behavior, radial behavior, spiral behavior and elliptical behavior of the system. Then for the nonlinear ordinary differential equation, we have discussed this Hartmann-Grobman theorem, and we will have like a hyperbolic nature or like non-hyperbolic nature based on this like real part of these eigenvalues. And then if this is a non-hyperbolic in nature, then we have included this Lyapunov function for the analysis of the stability. Then finally, we have discussed about null Klein, that is nothing but the phase diagram analysis based on null Kleins. And with this, we conclude our lecture. Thank you for listening this lecture series.